All right, today we're reviewing Chapter 6 on z-scores and the normal model. First thing we talked about in Chapter 6 is transforming data. So imagine you have a list of numbers, 1, 3, 5, 7, 9. What happens if you add or subtract something to the data? What happens to the center and spread of the distribution? Well, let's look at an example. If we add 1 to all of these, we end up with a 2, 4, 6, 8, 10 for our list. Would the mean change? Yeah, it would go up by 1. Would the spread change? No, the numbers did not get more far apart or less far apart. What if we were to multiply or divide all the data by something? What would happen to center and spread? Okay, so our new list would become 2, 6, 10, 14, 18. And so would the mean change? Yeah, it would be doubled. Would the spread change? Yes, now the numbers are farther apart. How much? By a factor of 2. Okay, so if we multiply or divide all the data by something, the center and spread change accordingly. If we add or subtract something to all the data, the center and spread, well, only the center changes, the spread doesn't. Okay. What if we were to subtract the mean from all of the data? What would the mean of the new list be? Well, when we added 1, the mean went up by 1. So if we subtract the mean would go down by the mean. So we'd have a mean of 0. If we divided all data in that list by the standard deviation, what would the new standard deviation be? Well, when we doubled our data, the spread doubled. So if we're dividing the data by the standard deviation, then the spread would change by being divided by the standard deviation. So it would be S sub x over S sub x, or it would become 1. So in general, when we do that, when we subtract subtract the mean from all the data and divide all the data by the standard deviation, we end up with a new list of data that has a mean of 0 and a standard deviation of 1. We can do this to any set of data, no matter the shape, distribution, units, or so on. Okay, if we then use the standard deviation as a yardstick to see how extraordinary a particular value is, we can compare values from any data sets, no matter how different the original distributions were. This allows us to compare 100-meter dash times in discus tosses, like we did in the pentathlon lab, to see which performance is more extraordinary, even though they're completely different events. To do that, we calculate what's called a z-score, standardized test statistic, and we do that by taking value minus mean divided by standard deviation. A z-score tells you how many standard deviations above or below the mean a result is. The farther away it is from the mean, the more extraordinary or unusual it is. Now, if you remember Chapter 6, you know that we use z-scores a lot with something called the normal model. You can use them without it, but if your data do fit a normal model, you can do a lot of extra things like finding areas under the curve. Normal model is one of many types of density curves. Density curves are used when the overall pattern of a large number of observations is so regular that it can be described by a smooth curve. The area under the curve is always 1. The area under the curve between any two intervals is the same as the proportion of all observations that fall within that interval. The median divides the curve into equal areas, and the mean is the balance or seesaw point. Median and mean are the same if the curve is symmetric, but if it isn't, the mean gets pulled in the direction of the long tail or the skew. Now, normal curves are a useful class of density curves because lots of data can be modeled by a normal model. They are symmetric, unimodal, and bell-shaped. They are described by the capital letter N, parentheses, mean, comma, standard deviation. These are parameters, not statistics, because we're talking about a normal model. Real data almost never is going to be perfectly normal. The points of inflection, which is the point on the curve on either side of the center where the curve changes from being convex to concave, those are both 1 standard deviation to either side of the mean. There are an infinite number of normal curves. The z-table in the back of your book is specifically for the standard normal curve, which has been transformed to have a mean of 0 and a standard deviation of 1. So if you ever want to do any normal model calculations using the table in the back of the book, you have to take whatever statistic you have and change it into a z-score. Then you can look it up in the back of the book. Now, if a normal model is appropriate, the 68, 95, 99.7 rule can be used to get a general idea of areas under the curve. And the 68, 95, 99.7 rule says that roughly 68% of observations are within 1 standard deviation above and below the mean. Roughly 95% are within 2, standard deviations of the mean, and roughly 99.7 are within 3 standard deviations of the mean. Now these are not exact, as we saw later when we did confidence intervals, but it's a general rule that can be used to give you approximate areas. So let's look at a problem. The distribution of heights for U.S. women can be modeled by a normal model with a mean of 64.5 and a standard deviation of 2.5. What percent of women have heights over 67 inches? Okay, well let's go calculate the z-score. 67 minus the mean, enter, divided by the standard deviation. So 67 has a z-score of 1. So if we then want to think of the normal model, just try to give a rough picture here. Negative infinity, comma 1. Okay, we have this normal model here. This is the point that we're looking at, and we want to figure out what percentile that's at, basically. Okay, well this is 1 standard deviation above, and we know that 68% of the area is within 1 standard deviation. So if this is the middle, this is the 50th percentile, half of 68 is 34. So this area over here is 34% of the area under the curve. So 50 plus 34 is 84%. So what percent of women have heights over 67? Well, 1 minus the 84%, right? Since this is at the 84th percentile, 1 minus 84, 0.84, excuse me. So that would be 16% of women have heights over 67 inches. And what percent of women have heights between 62 and 72 inches? Well, 62 minus 64.5 divided by 2.5. That's a z-score of -1. What about 72? Subtract, divide by 2.5. So between a z-score of -1 and 3. So let's make a quick picture of that. So -1, 3. So my window settings probably need to be a little bigger here. Let's look at it again. There, now we can see it better. So -1 here, 3 looks like it's going off to the very, very edge. Remember, this is an infinite curve here, but we just can't see that little part that's not shaded because it's 99.7. So what percentile are we at here? Well, this was at 50 minus 34, so this is the 16th percentile, and then this is 99.7% is between 3 standard deviations above and below. So if we look at 100 minus 99.7, that leaves only about 0.3% in either tail, and so 100 minus half of that, 0.15, tells us what percentile is up at the upper end. So 99.85, and then the other one was at 16, so that shaded area is about 83.8 something percent of the curve. So about 83-84% of women have heights between 62 and 72 inches. Okay, so that's how you use the 68, 95, 99.7 rule, but what if the z-score is somewhere between the standard deviations? So it's not exactly -1 or 3, it's like 1.2 or something like that. Well, let's look at an example. What if we want to know what percent of women have a height less than 5 feet? Okay, well the z-score comes out to be -1.8, calculated the exact same way I did before. Now you could go use a z-table and look this z-score up in the back of the book and get the area that way. You can also use the calculator. Okay, so I'm not going to make the picture again, I'm just going to go calculate the area. So to do that, I'm going to go to use normal CDF, and I need the lower bound of the shaded region, which in this case would be -infinity, so I just put -99999, comma, the upper bound, which in this case is -1.8, and there we get about 3.5, 3.6%. Okay. Now if you use the table in the back of your book, because those are rounded to 4 places or so, you might get a slightly different answer. Don't be too concerned about that. And same thing if you use the 68, 95, 99.7 rule versus using the table again or using the calculator. You're going to get slightly different answers, all that due to rounding. So don't be worried if it's a tiny bit different. If it's drastically different, you probably made a mistake. Okay, so there we go. Normal CDF, if you're using that on your calculator, that's fine. But when you're taking the AP exam, don't write just that. Graders are often trained to ignore calculator language. So you would say, I'm finding the area, explain what it is that you're doing. Or show in a picture, that I'm finding the area, of this shaded region and the area equals whatever. If you only write normal CDF equals whatever, they're going to pretend that they don't know what that means. Okay, so just be careful about that. Another example is finding normal percentiles. That's something else you can do when data fits a normal model. So blood cholesterol level in teen boys can be represented by a normal model with a mean of 170 milligrams per deciliter and a standard deviation of 30 milligrams per deciliter. Let's say we want to know quartile 1, which would be the 25th percentile. So in the Z table in the back of the book, we can look for 0.2500 or the closest number we can get to that in the Z table, and then go to the margins of the table to read the Z score. And then we can plug that into the Z-score equation right here. We could do that, or we can use the calculator to tell us the Z-score using inverse norm. Okay, so let's do that. Again, that's under the distribution menu. Inverse norm, 0.25, has to be put in as a decimal. And so there's the Z-score, negative 0.674489. And then if I want to figure out the actual value, I need to plug that into the Z-score equation. So now I'm trying to solve for x. So I'm going to multiply by 30 on both sides to working on getting x alone. Okay, and then I need to add 70 to both sides. So plus 70, or excuse me, 170. There we go. So the 25th percentile or quartile 1 would be at almost 150, 149.7 milligrams per deciliter. All right. Now, not every density curve that looks normal really is normal. Never say something is normal if it is really only approximately normal or is just unimodal symmetric. So if you don't know for sure that it's normal, say it's approximately normal or that it's unimodal and symmetric. If you need to know if something truly is normal, you can look at the shape of the histogram first and see if it's unimodal symmetric. You can plug data in and see if it fits the 68, 95, 99.7 rule. So find the mean and standard deviation of your data, and then what percent of the data are within one standard deviation of the mean. Is it about 68? What percent of the data points are within 2 standard deviations of the mean? Is it about 95? So on and so forth. Probably the fastest way would be to check the normal probability plot on your calculator, but it's a little bit hard to interpret at our level of knowledge in AP statistics. But basically you go into your stat plot after you have your data in a list, and you choose the last plot here. This is the normal probability plot, and make sure you have the list that you're interested in selected, and then zoom stat. Now, if you get this little error here, then just get out of that screen first and then zoom stat. Okay, and so what we're looking for is something that's a straight diagonal line. I do see a little bit of a bend to it here. So if this data is supposed to be exactly normal, well, this isn't. If I'm just looking for something that's approximately normal, this may be close enough. Okay. Now, if data are not approximately normal, you can still find z-scores and still talk about, whether one number is more extraordinary than another number. But you can't use the 68, 95, 99.7 rule or the z-table or normal CDF or any of those things to find probabilities, areas, or proportions under the density curve. You can only do that if you know that using a normal model is appropriate. All right, so that's our fast and quick review of Chapter 6, Normal Model Density Curve Z-Scores.